Okay. I think somehow that solved it. Let's see. Okay, cool. Wow, somehow let's just hope that the audio track is also somehow recorded. So before we start, 10 minutes late, as a matter of fact, two quick announcements. We do have some room collisions. We quickly look on the calendar. Good. There is, we cannot have this lecture hall today in 1 week. That is Monday the 18th. So we were provided a room or a seminar room at the university with 20 something, 3, 4, 5, 6, 7, 8, 9. Yeah, we could just barely fit in there. So there's a seminar room. I'm gonna have a look at this. If not, we'll just stream the next lecture. And then there's let me see. There's, let me go to my calendar. A second, good. Then there's Monday the 2nd of December. So they're both, Jesko and me are traveling. So for that date, we will skip the lecture, right? Whoops. Let's see what's happening. So, no, I want this. So we have Monday, 18th, remote lecture slash, let me give you the name of this seminar room. Okay. So this is seminar room 5 in E24, 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 seminar room 5. And says somehow 011. But says this is the E2 4. This seems to be the math building. All right, and Monday, the 2nd of December. Well, year already over. No lecture. All right, that is that. Back to the recording here. Okay, so that is that concerning organization. And I think there were some questions earlier regarding the content of last lecture. So is this something you would be comfortable to ask in front of the audience, or is this sort of just a one-on-one kind of question? No, both is fine.
No, actually, it is better to be asked in front of the audience, not because I believe most of the other students also.
Good. So where
what decision element problem.
Cool. Let's, yeah. Oh, I didn't. No, I think I also had it here, right? Here, this one, right? The algebraic geometric, let's say, understanding or a perspective on the Diffie-Hellman problem. So good, let's not draw it on the whiteboard this time, but take our space here. So let's say this is not what these vector spaces look like, right? But let's say we have ZP square, right? Pairs of ZP elements. And so down here, we're saying Diffie, do I have a laser pointer? Actually, does this one also work? But no, it doesn't. So let's use the software laser pointer. So we're essentially in the linear algebraic version of or perspective. It's the same problem, right? This is just how you interpret this problem. The question is, you're giving two-dimensional vectors. This guy here, it says log GG. Well, this is 1 and log GH, right? So you're having, what's happening? You're having a vector here, right? Let's call this guy 1 log GH. And now you're also having that guy here, right? And now you're having a second vector. Let's use a different color. Maybe not this. Maybe just red. And in one perspective, there's log G prime log GH prime. It's linearly dependent, right? It's just a scaling of this first vector. In the second perspective, it's just uniformly random. And the goal of the adversary is to distinguish which one is the case, right? You're being given a pair of vectors. So you're being given this, on the left-hand side, the adversary or distinguisher is being given this 1 log GH, comma, log, I mean, let's write it let's write it sort of like this. Here he's being given some S times 1 log GH, right? And on the right-hand side, he's also, the first one is kind of the same. Here's the same, right? It's just the same distribution. But here, the second vector is, let's say, just chosen uniformly random. Let's say U and V, right? And the goal of the adversary is to distinguish on which side he is. I'm giving you a pair of vectors and asking you, are we on the left side or are we on the right side? So, good. Now the question again.
Yep, I think this made it much more clear. Thank you.
I think it's the. Okay, then it's probably just a good thing to have it here on the slide, because I think I said exactly the same thing in the last lecture. But
I'm afraid I recall the two different cases of drawing. So I was like, I think you draw only one.
Could be that I just drew one picture, but again, I mean,
one X Y axis. So I was like,
just feel free to ask a question because this is sort of an elementary point, right? In a way, we'll think of these pairs of vectors now in this proof kind of as matrices, right? You're having a matrix. Here, the two columns are linearly dependent. So we're going to have a matrix of rank 1, whereas on that side, we're going to have a full rank matrix, a matrix of rank 2. Good. But yeah, that's really all. And that's, in a way, Kramer and Shoup sort of started this perspective on the Diffie-Hellman problem, right? Before that, people were thinking of that sort of in terms of, let's say, quadratic functions, right? Because I mean, this AB term you have up there is like a product function. It's a polynomial of degree 2, right? But as a matter of fact, the question is at its core linear algebraic, right? So when you give me, so what does this correspond to, right? Let's write this in a different color. And this is going to be quite important, right? You're going to have, this corresponds to GH. And here we're having G to the S and H to the S, right? And here again, GH. And now just two, let's call them capital U and capital V, two uniformly random group elements, right? In a way, I'm hiding a matrix or a degree or a linear system with two equations and two variables in a D-log group, right? So we can think of this cryptographic group that we have here as a way to hide a vector space. So you can still do linear operations on this vector space, but what can you not do? So again, we can, you're having sort of pairs of group elements. So you can, of course, multiply them together, right? And you can exponentiate. So you still have access to the group structure. But one thing you cannot do is linear algebra, right? You cannot do Gaussian elimination. You're having a matrix, right? The coefficients of this matrix are, so to speak, hidden in this group. Now you cannot turn this matrix into a triangular form, right? Because if you could, then you could easily distinguish these two worlds, right? So if I'm giving you a matrix of rank 1 or a matrix of rank 2, if I'm going to give you that in the clear, if you can do linear algebra, in particular divisions, right? And if you can clear out the rows and columns of the system, then you could easily distinguish, right? So in a way, right, since Kramer and Shoup, we think about cryptographic groups as a way to allow someone to still do linear operations, right? Since we're having a group, we still have linear homomorphism, but we cannot do linear algebra, because in order to do linear algebra, we would sort of, in a abstractly, not abstractly speaking, but in a certain sense, have to be able to invert a linear system, right? And one thing that would be necessitated here would be to be able to divide by some hidden values, right? Values that are hidden in this group, and that's exactly would correspond to solving, or we wouldn't know how to do that without solving a D-log problem, right? So that's the, in a way, the modern understanding of cryptographic groups. Allowing you to do linear algebra I'm allowing you to do simple computations on a vector space, additions, linear combinations, right? But nothing else, nothing more powerful, in particular, not linear algebra. Good. So in a way, people have been trying to abstract this out, right? To say, oh, look, hiding things in a cryptographic group is like just giving you black box access to a linear equation system. You can take linear combinations of rows and columns, but you cannot read what's in these rows and columns. And in fact, these models are useful, but these so-called generic models, right? There's this thing called the generic group model. For those who've heard this or worked before, this is like a random oracle model on steroids, right? There we can think of adversaries or algorithms being able to do group operations as they would expect, but not anything beyond group operations, right? So this is a way to really fully restrict an adversary to just do group operations and nothing beyond. Here in the DDH world, you're being given group elements, right? We hope that G to the S hides S or hides something about S, but we cannot really point down what precisely it hides about S. Right? What we can do is make concrete assumptions, such as the DDH assumption, saying GH, G to the S, H to the S is indistinguishable from GH, UV, where those two guys are just two random group elements, right? What's happening? Element G square, right? And here up here we're in a ZP square, just to see the difference. This is a capital U and capital V. Good. Are there any more questions? Because this is important.
There was a couple of questions about Shu specifically. Should I ask him now?
Let's maybe, yeah. Let's go into this. So.
Somewhere said parse the keys.
Ah, yes, exactly. So what does that mean? Good, that's computer scientist talk. So here, basically we're saying the public key is of the form, underline that, the public key is of the form KGHUVW, right? And when you're so who of you has programmed with Python? Who knows Python? Okay, then you would kind of be familiar with this notation of maybe not writing parse, but in Python, right? When you know a certain input of some function comes from a certain domain, you can write stuff like enc. If enc is now your algorithm, pk equals k g h u v w right comma m. This is basically on this scope here, right? I guess you're a mathematician, maybe, because I think mathematicians typically haven't seen this whole parse notation. Here on this scope, the values k, g, h, u, v, and w don't exist yet, right? I've defined them in this other algorithm here, but I haven't yet defined them in this enc algorithm. So I need to kind of declare to this algorithm, or in this case, the reader, right, or what form this public key is of, right? I mean, some people use dot notation, pk.k, pk.g, or whatever, but that's cumbersome, right? Does it make sense? Basically, parse mean this is a composite object, right? And now we're going to take we give these individual parts of this object individual names. That's all. Okay. I mean, I'm going to leave this here, but are there more questions? So yeah.
The last question is when we're computing beta, we're using hash function with key.
Yes. This should be this key, capital K. I think this is a typo. This should be. So why are we using a hash function with key? You're saying, why do you put a key into your hash function? Is this a question? Good. This is a very good question. Maybe let's quickly sidetrack. So why do we need keys for hash functions? Yes?
Perhaps the key is unique. Let's say it was the case.
No, look, the key is just chosen randomly here, yeah. Right? But
random, it's going to be different than the other keys of the same.
No. This has, okay. So there's two reasons why we choose keys for hash functions, right? There's a very theory reason and a very practical reason, but so one extremely theory reason and a pretty practical reason, but at their core, they are the same, right? So what would happen if we had an unkeyed hash function? Let's maybe start from the theory perspective. So who here in this course has taken one of the more advanced complexity classes with either Markus Bläser or Karl Bringmann? Okay, good. What's the good? Now you volunteered. What is? I mean, then you're familiar with the circuit model of computation that we typically use here in cryptography, right? Let's go back where we still have somewhat. We don't have a lot more. Can I maybe add a slide here? Let's see. Let me try to add one. No. Well, good. So let's maybe make this quick. The standard model of computation that's typically introduced in the third semester is Turing machines, right? Turing machines are the standard model of algorithms in computer science. It's just an object of constant size, right, that solves a problem or decides a language, as we say, right? So Turing machines are a uniform model of computation. We have one description of this Turing machine. This is just a single string of constant size, right? The constant bit can be very large, but that decides this language for any input length, right? Independent whether my input has length 100 or 2 million, it's the same Turing machine that runs or that decides this language, right? Hence we say it's a uniform model of computation. For every input length, it's sort of the same algorithm in the sense that decides this language. Now, when it comes to circuits, right, it's a bit harder because typically when we write down an algorithm as a circuit, it's clear that as a Boolean circuit, that this Boolean circuit only takes inputs of a certain length, right? If you have a circuit which has 200 input wires, you cannot feed this circuit an input of length 300. Does it make sense? So circuits are, as we say, a non-uniform model of computation. When we say a circuit decides a language, but a language is an infinite object, right? Typically, we talk about an infinite number of input lengths, right? In complexity theory, everything is asymptotic. So when we want to say a circuit decides something, that's sort of underspecified. We have to say infinite family of circuits decides a language. So for every input length, I have to give you a different circuit. Like where these circuits come from, that's the question now. Maybe the circuits are uniformly generated, and there's a Turing machine that writes down these circuits, but that would mean you can directly run this Turing machine somehow, sort of just simulate these circuits, and you're good. So when we talk about circuits, we basically mean when we talk about circuits, we mean for every input length there exists a circuit, right? And there exists a circuit when it comes to something like hash functions is now troublesome, right? Because if you had an unkeyed hash function, right? How could I now build an adversary? Remember, an adversary is just an infinite family of circuits, each of polynomial size in the input that solves a problem, right? So what's the problem when we talk about unkeyed hash functions? When my hash function is most hash functions or all hash functions constructions that we have in cryptography are uniform, right? They can be written down as a as a tiny Turing machine, as an algorithm, as a C++ program that's the same as a Turing machine. I'm hoping I'm not telling you new things here, right? That a C++ or Python program is essentially a Turing machine corresponds to a uniform model of computation. What's the problem if we have an unkeyed hash function? Right? Remember, the goal of an adversary is just to find a single collision, right? What's the problem with uniform or with unkeyed hash functions when we have a non-uniform model of computation? So maybe see if I have some more space. Is there more? Yeah, let's just use this one here. So basically, for each input length, right, we have a different circuit, say, C1, C2, C3, C4, and so forth. They each are of, I mean, we're having an infinite family, right? Let's say C lambda. And the only thing we know that when we look at this, the size of C lambda is bounded by some polynomial in lambda, right? That's the only thing we know, but otherwise there's an infinite family of circuits. And when we have an adversary that breaks an assumption, then what this says is there exists an infinite family of circuits or an infinite sequence, right? When we say a family of circuits, we mean an infinite sequence, one circuit for each input length that solves a certain problem, right? That's sort of the non-uniform perspective, okay? So what does that mean for hash functions? Right, when I'm having an unkeyed hash function, keyed hash function, let's say h, which maps inputs of arbitrary length, right, to, let's say, 0, 1 to the lambda, right? So or 0, 1 to the something. What can we do here now? Or what could such a non-uniform adversary do, right? And recall, we say a hash function is insecure, right? That's always important to keep in mind. What does it mean to be collision resistant? Well, we define the notion of collision resistance by what it means to be not collision resistant, right? A hash function is not collision resistant if there exists an adversary, a PPT adversary. PPT adversary means, in this case, an infinite sequence of circuits where each is of polynomial size, right? Such that when I'm feeding this, when I'm giving this algorithm, this circuit, a hash function or a problem of size lambda, he outputs a hash collision, right? So good. What can go wrong with an unkeyed hash function? Well, again, this function here doesn't have any randomness, right? No randomness, right? Because there is no key. The key is what randomizes a hash function. And what this circuit, what now happens when we have an input or inputs of length 2 lambda, right? When we restrict ourselves to inputs of length 2 lambda, right? Let's say we just consider, let's call this h2 lambda, right? Whoops, which is what's happening. We restrict ourselves to inputs of length 2 lambda. What do we then know about the existence of collisions? A function which maps 200 elements into, or let's say 100 elements down to 10 elements, right? What do we know about the exist? Yes?
There must be at least one collision.
There must be collisions. As a matter of fact, we can say there good. But if our hash function goes from a big domain in a small domain, too close, then there must be two different inputs that map to the same output, right? So let's call them x0 and x1, right? We know these two guys exist. We don't know of a way to find them, but we know they exist, right? And since, again, there is no randomness, our C lambda could just do the following. Output these x0, x1, right? This is the thing with asymptotics. So those are these two guys here, right? That's the problem with this non-uniform model of computation. You can think of these circuits as, well, an efficient algorithm which for each input length can get a so-called advice, right, of polynomial length. And in this case, the advice is just the hash collision. Okay, that was a very theory perspective on this. Of the practical perspective on this, let's say we have a hash function candidate, SHA-2, right? And people all over the world use it unkeyed. Okay, no one uses it with a key. How do you key SHA? Sort of a compression function like SHA. How do you do that? SHA is just a function that maps 200, let's say 512 bits down to 256 bits, right? So how do you turn this into a keyed hash function? Yes.
You can just prepend the key.
Exactly. So in the world of, I'm quickly going to repeat this in case not everyone heard this. You said you can prepend the key with a random string, right? And this random string is the key, but in the world of hash functions, this is typically called a salt, right? You're salting the your input to randomize it, right? But this is exactly the same as keying your SHA hash function. Good. If you were not going to do this, if you were not salting your hashes, then it would be enough if someone with an insane amount of computational power somehow finds a hash collision, right? And now this hash collision, which maybe happened in a, I don't know, they really spend a lot of energy and effort to compute this. Now this can be reused over and over and over again, right? So someone who can pre-compute a hash collision could now, in concrete terms, amortize the costs of computing this. Whereas when we have a keyed hash function, every time someone chooses a new key, they would have to compute a new hash collision. Does it make sense? Right? So if we were to use in practical terms, but this is exactly sort of the same reason as in the theory setting, in the when we said a hash collision could be given by a non-uniform advice. We can always think of such a non-uniform advice as the result of some massive pre-processing stage, right? And that's exactly for that reason that we really don't know how secure our components are, right? The minimum we want to be able to say, that's why we adopted this non-uniform model of computation cryptography, is that if there's an adversary who attacks our system, there are no all for the of one attacks. It should not be possible to just attack a single object and then leverage this, right? Leverage the result of this attack over and over and over again to attack any number of users of the system, right? Every single attack you're trying to mount should be as expensive as possible. Shouldn't be possible to amortize the cost of an attack. I hope that sort of makes it clear why we need keyed hash functions. Unkeyed hash functions are really bad. More questions? This was a bit of a detour, but we're ready for. Okay, good. We are already 45 minutes. Let's maybe since I started late, you may forgive me if we go back to the proof of Kramer-Shoup. All right, let's quickly again go over Kramer-Shoup encryption, right? It was sort of like a more complicated version of El-Gamal. El-Gamal, our key was just G, H, where H was G to the X, but here we're actually choosing a 6-tuple of group elements, X1, X2, Y1, Y2, Z1, Z2, and instead of just computing a single public key, the public key now kind of consists, morally speaking, of these group elements U, V, and W, right? And U is G to the X1, H to the X2, V is G to the Y1, H to the Y2, and W is G to the Z1, H to the Z2, right? And we additionally put this key for the for a hash function into both our public and secret keys. To encrypt, right, we choose ourselves a random R, just as in El-Gamal, but now we compute a G hat, which is G to the R, H hat, which is H to the R, and a third value U hat, which is U to the R, times actually the message M. And now we just hash these three group elements together, get a beta, and compute this T as V times W to the beta exponentiated to the R. We call this the proof part of our ciphertext. And our ciphertext is now G hat, H hat, U hat, and this proof part T. Good. Now, decryption, right? Or what do? We first recompute this beta, because G hat, H hat, and U hat are just being given in the ciphertext. So we can recompute beta, it's beta prime. And now we test whether this T is identical to G hat to the Y1 plus beta Z1 times H hat to the Y2 plus beta Z2. And if so, right, we just compute U hat, I mean, if not, we output but if so, we output U hat times G hat to the minus X1 times H hat to the minus X2. And we've seen last time, right, so first of all, that if everything is run correctly, the proof T that's computed by the encryptor is the same as what the decryptor computes, right? This is, I mean, what gave this technique that was introduced by Kramer and Shoup the name hash proof system, right? On the left-hand side, we're just being given, let's say, collapsed values, these U and V. Actually, this is very hard to read here. This U times W to the beta. Let's maybe, yeah, this W doesn't look good. Now it's better. Okay. As a matter of fact, again, there is this way of computing these proofs in two different ways, right? On the left-hand side, or how the encryptor does it, is using the yes question.
Sorry, is it possible to dim the lights?
Let's see. It should be. I hope it is. Better. All right. So here on that side, right, we're using the knowledge of R, and recall R is sort of the random value chosen by the encryptor, so the decryptor doesn't know R. On the other hand, right, the decryptor uses Y1, Y2, Z1, Z2. Those two are not accessible to the encryptor, but those four are not accessible to the encryptor, right? So there's kind of an asymmetric way of computing this proof. Great. Okay, now we've done this. And finally, let's get into security. So we have the following theorem, which states that given that our hash function h is collision resistant, and that the DDH is hard, typically we say, we're a bit more precise, we say in G, right? Because, I mean, typically you have to specify in which group you assume that DDH is hard, but we call this group G. Then the Kramer-Shoup crypto system is in CCA2 secure. So it satisfies the stronger notion of CCA security. And naturally, this is kind of there's several moving parts in this construction, right? So we have the group and we have a hash function. So we have at least two components, and whenever we want to prove security of a cryptographic scheme that's in some sense composite, this of course calls for a hybrid argument, right? So we will successively modify the security experiment, in this case the InCCA2 experiment, into a more ideal experiment. And in each step, we kind of want to get rid of one of our assumptions and let's say kind of make the adversary's life harder, such that once we're in the last hybrid, his goal is impossible, right? So how does this paradigm play out in the case of Kramer-Shoup, right? As usual, let's just again, a hybrid argument, or all proofs in cryptography, almost all proofs in cryptography are proofs by contradiction, right? So assume towards contradiction that we do have a PPT adversary A1, A2, right? We said this adversary has two stages, which breaks the InCCA let's add 2 here, 2 security of Kramer-Shoup with non-negligible advantage epsilon, right? Let's assume our scheme is insecure, and let's lead this to a contradiction via a sequence of hybrids. So first off, we start with the real experiment, right? So before we do any modifications, let's just recall how this InCCA2 experiment looks when we instantiate this with Kramer-Shoup, right? And really the only thing that kind of matters here is the challenge ciphertext, right? So we do know that the public key PK is this K comma how did I call them? You had let me just yeah, I think so I'm not exactly. So the public key was just GHUVW, GHUVW, right? This is of course also in the view of the adversary. And again, the thing that matters that we're gonna modify in the sequence of hybrids will be the challenge ciphertext. Everything else, a question? No. Everything else will be left untouched, but in the real world, right, the challenge ciphertext depends on this challenge message MB, right? This MB is the only component of this ciphertext that depends on the challenge bit B. Recall, the goal of the adversary is to guess the bit B, right? The experiment flips a random coin, and if it's 0, it encrypts M0. If it's 1, it encrypts M1. So our goal will be to get rid of this MB somehow, right? Since once this MB is gone, the best thing an adversary can do is guessing, right? Then if nothing depends on B, if nothing in the challenge ciphertext depends on B, then the adversary has to guess blindly. That's our strategy, right? So, and again, let's recall our challenge ciphertext. Now let's call it G hat star, H hat star, U hat star, and T star. And the randomness we use here, let's call it R star, right? So G hat star is just G to the R star, and H hat star is H to the R star, and U hat star is U to the R star times MB. And of course, we are also using R star in the computation of this proof T star, right? Where we also use beta star, which is just the hash of G hat star, H hat star, and U hat star. Good. That's the real experiment. We haven't done anything yet. All right, nothing happening here. And now let's go to hybrid H1. Now we're gonna do a modification. So here, hybrid H1 will be exactly the same as H0, except that the experiment aborts and outputs a random bit, or right, something uniformly random, if our adversary A sends a decryption query G hat, H hat, U hat, comma T, where this first triple G hat, H hat, U hat collides with this V3 here taken from the challenge ciphertext. So this is easy for phase 2 queries, right? Because in phase 2 queries, we have already computed our challenge ciphertext, right? So in phase 2, or at the end of phase 1, the adversary announces M0, M1, and sees a challenge ciphertext, right? It sees this G hat star, H hat star, U hat star, T star, right? What do we say here when we mean HK of G hat star HK of G hat, H hat, U hat is the same as HK of G hat star, H hat star, U hat star. We say the adversary aborts it. I mean, easily in phase 2 queries, we can test this immediately. What do we do with phase 1 queries where we don't yet know what what this G hat star, H hat star, and U hat star is? Saying we also abort them. How do we do that? How can we abort if a query collides with something that which we don't know yet? It's the easiest thing to do. Any guess? Just postpone abort to to that point in time when we compute the challenge ciphertext, right? So of course, we cannot abort yet before computation of the challenge ciphertext. But when we compute the challenge ciphertext, which includes this G hat star, H hat star, and U hat star, we just test if G hat star, H hat star, and U hat star collides with any of the G hat, H hat, U hat that were queried by the adversary to the decryption oracle before, right? So what we have to do there is we need to record all of all of A's decryption queries in phase 1 and test for collision after generating the challenge ciphertext. Okay, does it make sense? Good. That's what we mean when we say also holds for phase 1 queries. Okay. So we have H0 and we have H1. And how can we show that those two experiments are indistinguishable from the adversary's view? What's the suggestion? Anyone? First question we ask ourselves is, in order to distinguish these two experiments, right, because we haven't really changed the challenge ciphertext. All we have done is saying that if a certain event happens, then the adversary just outputs a random bit. Okay, so what we could and what we will do now is to say that, well, if the adversary actually manages to provoke this event, right, then he has to be able to do something magical, right? On the other hand, what happens if let's say we have an adversary who never manages to trigger this event? What happens then? What happens then from the view of the adversary? What can we say? Let's say we have an adversary who never manages to trigger this abort event, right? Who never manages to make the experiment abort and output a random bit. What can we state holds from the view of this adversary? Yes?
The advantage doesn't change.
Exactly. The advantage is identical. So unless the adversary makes this event trigger, right, the two experiments, H0 and H1, are perfectly indistinguishable from the adversary's view, right? Nothing is different. In other words, the only way to distinguish these two experiments is to make this event trigger, right? Is to send a decryption query C, which collides with a G prime G hat star, H hat star, and U hat star under this hash function. Okay, so and that's what we're going to use, right? So good. Now, assume A distinguishes H0 and H1 with advantage epsilon 1, right? In a way, it just means that the advantages of A in hybrid 0 and hybrid 1 are just epsilon 1 apart. Take the difference between these advantages. Let's assume that's greater equal than epsilon 1. Then the event that A makes a query with, let's say here, non-negligible, then the event that A makes a query decryption query, sorry. G hat, H hat, U hat, T with HK of G hat, H hat, U hat equals HK of G hat star, H hat star, U hat star. Then the must happen with non-negligible advantage. Well, something O of epsilon 1. In fact, it's something like epsilon 1 half. The precise constant, yeah, it's either epsilon 1 or epsilon 1 half, but it's good enough, O of epsilon 1. And this conclusion, let's say, I'm finalizing an exercise sheet. I'm going to add that to the exercise sheet, right? That we're going to see how this works. So let's see. Let's assume we good. Let's say we are here. All right. So what can we say now? What can we use such an adversary for? So we have an adversary which somehow magically, right? Or when we play H0 versus H1 with this adversary, or let's say when we play just H0 with this adversary, then somehow magically with non-negligible, that is a substantial probability he sends such a query G hat, H hat, and U hat, which collides with G hat star, H hat star, U hat star. How can we now use this adversary to do something really surprising? Any yes? Exactly. So this adversary finds a hash collision, right? So but in the when we want to find a hash collision, so now we want to use this adversary to build another adversary that is just given a key of our, let's say now adversary B of K. So this adversary is just being given a key K for the hash function, and his goal is to output a hash collision. What does this adversary do? So we want to use A, right, the adversary that kind of distinguishes between hybrid 0 and hybrid 1 with advantage epsilon. And we want to use him to build such an algorithm here, right? Because that's what we do in computer science. We're given one algorithm and show that then, or let's say in theory of computing, right? We assume we're being given an algorithm who does one thing, and we build another algorithm who does something else, but which is contradicting our one of our hardness assumptions, right? So what does this algorithm B do? Nothing spectacular. Yes.
You mean the building this adversary builds the if you have the key assumption around the first adversary?
Yes, that's what we're doing simulation, right? The magic word in kind of not just crypto, but all of theoretical computer science is we take this algorithm B and we let him simulate for our adversary A the hybrid H0, right? So this algorithm B just runs what does it? Oops. So it simulates H0 faithfully with A, except what? So we simulate the INCCA experiment and recall that in the INCCA experiment, the first thing we do is run the keygen. We're simulating it as is here for Kramer-Shoup, except we're going to change one tiny aspect. Which aspect is this? What are we going to do different? Yes? Exactly. So instead of letting the keygen algorithm choose the key K, the reduction or the adversary B takes the key K, then it's being given. I mean, we have the promise that this key has been chosen uniformly, right? Because keys for hash functions are chosen uniformly. And we're just using this key K that we're being given. Except that we use the key K in given to B. Given to B instead of choosing a fresh K. So what can we say, right? I just said it. This key K that's being given to our algorithm B is chosen uniformly random, right? Because that's how the collision game works. We choose a fresh uniformly random key, give it to the adversary has to output a hash collision for that key, right? So what we can say is simulation of B is sorry, that was a bit too fast. Good. Once a collision G hat H hat U HK of G equals HK of G hat star H hat star U hat star occurs, output x0 equals G hat H hat U hat, x1 equals G hat star H hat star U hat star. Okay, this is what our collision finding adversary does. Okay, now I would really like to insert, can I somehow duplicate this slide? Why do I only... okay, here. Let's try that. Good, let's say... can I say duplicate? Yes, I can. Perfect. Good. Okay. Perfect. Okay. Now, first thing that we notice is that BK simulates H0 perfectly from the view of A. Correct? We said that because this K that B receives as input is uniformly chosen, so A cannot tell the real experiment H0 and the simulation by B apart. They're identically distributed. But that means since those experiments are just the same, this event that A makes a decryption query like this must also happen with probability O of epsilon 1. Okay? So since really those experiments are the same, that means that this event that we just considered must also happen in B's simulation. Yeah. A produces collision G hat HK of G hat H hat U hat equals HK of G hat star H hat star U hat star with non-negligible probability O of epsilon 1, but this is a contradiction to collision resistance of H. Yes.
The indistinguishability between H0 and H1.
What it means? Okay. I mean, essentially, what means those two hybrids are indistinguishable, right? So I have H0 is the original in CCA experiment, and H1 is the in CCA experiment with a small modification. So now we can wonder, does the advantage of the adversary change when we go from H0 to H1? Right? In H0, that's one experiment, the adversary has a certain advantage. We call that epsilon. Right? And now we can ask, when we go to H1, does the advantage change? I mean, if it gets worse, that doesn't help the adversary, right? So we could ask ourselves, is the advantage of the adversary in H1 something like epsilon plus epsilon 1, right? So if this is the case, we can use this adversary to distinguish these two experiments with advantage epsilon 1, right? Then we have a distinguisher. You know what? Let me also put a note here. Let's make an exercise for that. Good. That's essentially what we mean that when we say an adversary distinguishes two experiments with a certain advantage, right? So basically, when we go to H1, his advantage cannot improve by more than a non-negligible amount. Good. Okay, so now hybrid H2. This is now the same as H1, except that we change something about the challenge ciphertext. Okay, so instead of computing this proof T as or T star as V times W star, V times W to the beta star to the R star, we set T star as this. Okay, so Why does this hold? Right, we're still just changing the experiments. So why what happens now? What happens between H0 and H1? So asked differently, where do we compute T star like this, and where would we compute it like that? Good. And what can we say about these two values? Recall this is the challenge ciphertext. This is not the ciphertext generated by the adversary. This challenge ciphertext is produced by the in-CTA experiment, or in this case now H2, right? What do we know about these two values? Right, and we do know, or recall that the experiment needs the secret key. It needs this Y1, Z1, Y2, Z2 to answer decryption queries, right? So whenever the adversary sends a decryption query, the experiment touches these values anyway. So what do we know about these two values? Yes?
They should be equal.
They are equal. So we have seen in the correctness proof earlier, meaning last time, that this B times W to the beta to the R is the same as G hat Y1 plus beta Z1 times H hat to the Y2 beta Z2, right? Those two values are the same. Whoops. No. Where did I jump now? H0. Good. Nah. Good. Those two, this is like in ENC, like, whoops, in ENC, and like in DEC, and they are identical. See correctness. So if these two values are always the same, what does that mean about the distinguishing advantage of our adversary A between these two experiments? Really, all I've been doing is I'm computing a function differently. Still the same function, I'm just computing it differently. Can the adversary see this? No. So from the view of the adversary, hybrid 1 and hybrid 2 are identically distributed. That means he has a distinguishing advantage of 0. The view of A, H0, and H1 are identical. Great.
H2.
Oh, what did I say? H1 and H2. Thank you. H1 and H2 are identical. Perfect. Good. Okay, this we actually don't need. And now we come to hybrid H3. So H3 is the same as H2, but now we again compute our challenge ciphertext C star a little bit different, right? Instead of choosing recall in H2, right? We compute G hat star as G to the R star, H hat star as H to the R star. Instead, we're choosing the uniformly random, right? So in H2, this vector g hat star h hat star is linearly dependent with my vector gh. Now I'm choosing it linearly independent. What can I argue here? Any ideas? What? Yes?
Adversary should not be able to distinguish.
Why not? So let's say you can distinguish. What happens then?
He breaks the
Exactly. Breaks DDH. So again, the way we're doing this is via a reduction, right? So in this proof, I'm going to make all the reductions explicit. In the future, I'm saying this is a routine reduction to DDH, right? But again, the reduction is simple, right? Assume A distinguishes H2 and H3 with non-negligible advantage epsilon2, right? Then we can build a distinguisher against DDH. So let's call this algorithm D, right? So not so nice. D, and my algorithm D gets as input G comma H, G hat star comma H hat star. Already, or let's call them differently. Let's call them G prime and H prime. But this already spoils everything. G prime comma H prime, right? He gets this 4-tuple of group elements, or essentially 2 vectors, GH and G prime H prime. And what does D do now? So how can we now, what we want to build is a DDH distinguisher, right? So this D is a DDH distinguisher D. What does this D do? Right, because a DDH distinguisher is just being given a DDH challenge, which is this 4-tuple of group elements. So what do? What does my algorithm D do? And just a reduction, right? What? Yeah, but how? I mean, we need, so we're being given this adversary H, sorry, A, which has, let's say, this advantage epsilon2 to distinguish between our experiments H2 and H3, right? So how, given this adversary, how do we build this distinguisher D?
we build the distinguisher. We build the distinguisher on top of the adversary first of all.
Yes.
And
so how
we give the G and G prime, and then adversary gives us the difference.
Difference?
Is it correctly? Like, so we have to distinguish G and G prime, right? The distinguisher's job is to distinguish GH versus G prime, H prime. And we
the only thing that changes is one in one setting, right? G prime H prime is G to the S H to the S, and in the other case they just chosen uniformly random. So those are the 2 cases, right? So how do we use our adversary to break DDH? I mean, we're not doing something complex. We've seen a reduction earlier, right? So what's the natural thing to do?
send it to adversary.
Oh, I mean, how did we say it last time? We said we simulate an experiment, right? So what D does is simulate H2 faithfully, except, right? And now let's maybe go back. Into the keygen. What are we going to do different in keygen? Yes?
Instead of choosing G and H, perhaps we get the G prime and H prime.
Exactly. So instead of choosing in keygen, instead of choosing fresh, maybe I'm going to leave this open. It's probably easier. Instead of choosing fresh GH in keygen, use G comma H given to D. What do we do with G prime, prime and H prime? Let's again go back to the what are we going to do with G prime, H prime?
G hat or
So no, our algorithm is being given this G prime, comma H prime. What are we gonna do here? Maybe. So how good to simulate the challenge ciphertext? We need to somehow cook up G hat, H hat, and U hat. How are we going to do this? So, any suggestions for G hat? Yes?
well, I'm assuming since we give G prime as G, now we will give the G as G to this.
So G hat, how do we choose G hat in this reduction?
We give the G itself.
G, but I mean G hat is G, right? So here this would be easily distinguishable if it was G itself. So the reduction has already used the G comma H it was given. Now we have G prime H prime. What are we going to do with them? So how are we going to choose G hat? I heard something. Can you maybe say it loud? Good. So we set G hat to G prime and H hat to H prime. Still, what are we going to do with our U? Still have one thing to do with this U, right? So this U hat is U to the R, right? But the reduction doesn't know R. It's just being given some G prime, H prime, and in one case this is just G to the R, H to the R, in the other case uniformly random. So what are we going to do with how are we going to cook up this U prime?
Is it random?
No, we could set the message M to 0 and then the R isn't relevant.
No, but the message is still chosen by the adversary, right? So the adversary chooses M0 and 1. And no, it's, as a matter of fact, rather simple. Let's just remember how we chose U, right? So basically, U is G to the x1, H to the x2. Right, let's go back down here. Whoops, here. So first set G hat as G prime, H hat equals H prime. And now recall, right, that U is G to the x1, H to the x2, right? So how can we therefore simulate U, whoops, U hat as U to the R? How can we simulate this? Yes,
You use G prime to the x1 and H prime to the x2.
exactly. So we can write this as just G to the x1, H to the x2, right? But to the R. But this is just G to the R to the x1 times G, H to the R, sorry. H to the R to the x2, right? And these we're just gonna replace with G prime and here H prime, because we set G hat to be G hat, which is supposed to be G to the R. We set it to G prime, and H hat, which is supposed to be H to the R to H prime, right? So, and now set, I mean, in U hat, we of course have to also times MB, right, times MB times MB. So this is now G prime to the x1 times H prime to the x2 times MB. Okay, but on the other hand, now let's see who paid attention. What is, whoops, exactly. So what's happening to my T, right? T, what do I do with that, right? There it says use V times W to the beta to the R. Who paid attention? What did we do with T or T star? Yes. Exactly. So our T star is not an issue because recall earlier we just said, well, our T star is just G hat star times values that exponentiated with values that we know times H hat star exponentiated with values that we know. And by the way, here I think I forgot to write a star. Good. Okay. And now output whatever A outputs, right? We know this is a bit. Is a bit. Okay, this is now our distinguisher. Okay, now what can we say? Let's see if I have another. No, I don't. So I need to copy or duplicate. By the way, what time is it? Ooh, we're almost through. I mean, but it's I would say it's important to take our time here because this is kind of a crucial proof here. So what are we going to do now? We're basically now going to analyze the advantage of D, right? Analyze distinguishing advantage of D. Therefore, we're going to go into two cases. In the first case, we have G prime equals G to the R, H prime equals H to the R, right? This is the first case. A DDH distinguisher either gets GH, G to the R, H to the R, or GH UV, uniformly random group F. What happens here? What can we say here? Recall we want to say something about simulation, right? Our distinguisher D simulates something. What is D simulating in this case? If its input, right, it doesn't know what its input is, but let's say now, so our distinguisher D doesn't know what this R is, right? But let's just say for a moment, G prime is G to the R, H prime is H to the R. What's happening? Come again?
H0.
Not H0. So the two experiments in question here are, whoops, too far, H2 and H3, right? So we're talking about being able, our adversary being able to distinguish H2 and H3. So in the case that G prime is G to the R and H prime is H to the R. Exactly. So in this case, D of G comma H, G prime, H prime simulates H2 perfectly. Right? All the values that it's or the entire from the view of the adversary, these two experiments are the same. We just computed things differently, right? We just noticed that our distinguisher D doesn't have to know R to simulate this challenge ciphertext to our adversary, right? It can just do so by blindly given G prime and H prime. So in the by the way, now going back, we're not just choosing those two uniformly at random. We also have to say and set what we did here. U hat star equals G hat star to the x1 times H hat star to the x2 times MB. This has to be done in the hybrid switch as well. Good. So again, case one, we're simulating H2 perfectly because all the values are identically, all the challenge ciphertext and the key are identically distributed as in H2. Now we have case two, G prime, H prime are chosen uniformly. What happens now? Well, let's look at this. This is H3, right? If G prime and H prime are chosen uniformly, then also our challenge ciphertext, G hat star, H hat star, or these challenge ciphertext components are chosen uniformly random, plus we choose U hat star in this way. Does it make sense? So in the second case, when G prime, H prime are chosen uniformly, then what our distinguisher simulates is exactly perfectly. Okay, but that means if our adversary had a distinguishing advantage between these two experiments, then this immediately translates into a distinguishing advantage for D. That means distinguishes DDH with non-negligible advantage epsilon 2. This is, of course, contradiction against hardness of DDH. Ness of DDH. Hey, I think we're already over time. The last thing that's missing is just hybrid 4, right? And this is precisely the point where we will go into this linear algebra perspective of the, let's say, the DDH problem. As a matter of fact, we already got rid of the DDH assumption. So here, this will now just be a linear algebra argument, right? So the last thing that's missing is a simple linear algebra argument. But for today, time is over, and we're going to continue with this next time. Yep. Thank you.